All right, this is part 2 of a little bit on energy. This side of the notes, I just did this on the back of my sheet, and really it's just talking about specific heat. So it's something that we're going to hit on in climate in just a few days, probably a week after we do these energy notes. What I'm doing right here is I'm just drawing myself an axis. I want to draw a graph for you. So down here I've just got time. And if we were in class, we would be doing a lab on this for today. All I'm going to do is draw the graph that we'd get if we did the lab. So this is just increasing energy over here. Increasing energy added. Now, the two important temperatures that I want to have here, increasing energy is just going to go up. I want you to note, I should have had a ruler here, but it's all the way downstairs, which seems really far right now. We have 0 degrees Celsius, and let's put 100 up here. Now, probably what you're already catching on to is the fact that I have two different temperatures over here. I have 0 degrees Celsius and I have 100 degrees Celsius, and both of those are significant because this 0 is the water or the temperature at which water freezes, and 100 is the temperature at which water boils. And I know that you already know that. So this is actually just going to be the phase change of water. So it will be something that I think you're familiar with, but probably haven't seen for quite a while. So if we start our temperature at below 0, if we start it at freezing, this actually is really, well, it's really just going to be solid. This is our solid down here. This is solid, and if we talk about this being water, this would be solid ice, or solid water, it would be ice. And as this ice melts, I want you to notice that there's going to be a horizontal line there. So it's going to take a little while to melt. And that sort of makes sense. Just, you know what, I actually think about it making more sense when this water takes a while to freeze. Like if you put water into the freezer, liquid water into the freezer, it won't just be ice instantly, right? It takes some time to be able to freeze into ice. And likewise, it takes some time for all of this to happen. All right, so that's what our heat curve looks like. So just to orient yourself, I had solid ice down here. I'm going to have liquid water right here. So that makes sense, right? If water freezes at 0, then it's going to be solid below 0. It's going to be liquid above 0. And then at 100 degrees, what starts happening? The water starts boiling, and really what's happening is it's vaporizing. So it's changing into water vapor. So we have all 3 phases of water on this one graph. We have solid ice down here, we have liquid water in the center, and we have water vapor on the top. All right, so really quick, I want you to know we need a direction on this, first of all. I need you to understand that if we go up the graph, we're adding heat. So heat is going to be added. I know that sounds pretty obvious, but once we start doing problems with this, this will be very helpful. And then once we go down the graph, this is going to be heat energy released. And this is represented with a negative. All right. So we've got heat energy added if we go up the graph from solid to water vapor, which makes sense because if it's below 0 to above 100, heat energy is going to be added to increase that temperature. And then once we go down the graph, heat energy is going to be released. Okay. One thing I want you to notice is these flat lines here. I want to label these. So if we go up the graph, if we go from solid to a liquid, we call this from solid to liquid, we call that melting, if we're going up the graph. And if we go from liquid to water vapor, we call this evaporation. And if we go down the graph from water vapor to liquid water, we call this condensation. And when we go from a liquid to a solid, we call this freezing. And what I want you to realize is that we actually have to store up energy in order for all of this to happen. And this is on the front. So this is all on the ESRT, page 1. Right on the front, there's a chart. And it's actually going to tell you that in order for evaporation to happen, our water needs to save up 2,260 joules for every gram of water. All right, so it needs to save up energy in order to heat up or evaporate water. In order to condense water, if this is positive, you guessed it, it's minus 2,260 joules per gram. Okay? And then down here, notice my line is shorter over here for freezing and melting. It's actually because it doesn't take as much energy to save up. So for every gram of ice that's melting, it actually needs to add 334 joules per gram of that ice. It needs to save up some energy, almost like you're saving up money to buy that new iPhone that you've been wanting. And likewise, this freezing is giving off 334 joules per gram when it's going from that liquid to the solid. So I want you to notice that on this side I have minus signs because the energy is being released as we go down the graph. And on this side of my graph I have plus signs as we go up the graph and heat energy is being added. Okay, so I want to give you guys some sample problems for this because that all probably makes sense, but let's actually give some numbers with it, all right? So let's take, we're going to take an equation. We have Q equals Cm delta T. Sorry, delta T. I'm just going to put little multiplication signs. I'm not going to. All right, so C is the specific heat of something, of a substance. The M is the mass of something, an object, whatever we're heating here. The delta T is the change in temperature. And the Q is the heat energy. So Q equals the heat energy. So we have Q equals Cm delta T. I'm hoping you guys have done this before. I'm not totally sure you have, but we're going to give it a try anyways. So let's say I take the specific heat of water, which actually happens to be 4.18 joules per gram degrees Celsius. Now, this is actually a given, meaning we look this up in the chart or it's given to you in a problem. And let's say we take 100 grams of something. Okay, so Q equals 4.18 joules per gram degrees Celsius. My mass, let's take 100 grams. And let's take this 100 grams and let's go from 10 degrees Celsius to 80 degrees Celsius. Okay, so on our graph, we're going from 10 to 80 with 100 grams of water, which is about 100 milliliters. It's a graduated cylinder in our lab. So we're going to multiply this by the change in temperature, which would be 10 to 80, which would be a 70-degree change. I'm running out of space over here. So that if I just went ahead and did this and I inserted my numbers, 4.18 times 100 times 70, my number would actually be 29,260. 29,260 joules. Joules is just a measure of heat. All right. Let's do one more. Let's do ice. Let's say we change our ice from -10 to 0. Okay, so we're going to use the same equation right here. And we're going to do Q equals Cm delta T. Remember how I said that C was given? That's going to be given to you. It's 2.11 for ice. Joules per gram degree Celsius. Our mass, want to use 100 grams again? Let's use 100 grams. 100 grams. And what did I say? Let's go down into our solid ice here. We're going to change our temperature from -10 degrees Celsius to, I don't know, what do you want to go to? -4? -2? We go right to 0. Now let's go to -2. -2 degrees Celsius. So if we're going from -10 to -2, that's a change in 8 degrees Celsius. So let's go ahead and plug this in. Q equals 2.11. I'm going to drop my units real quick. Times 100 times 8. So 2.11 times 100 grams, because that's the mass of our ice, times 8 is 1,688. Sorry, that's joules. That's why you don't ever drop your units. It's bad habit. All right. So you can clearly see that to warm our water up from 10 degrees to 80 degrees, it's much more heat is needed than to warm our water up from -10 to -2, or warm our ice up from -10 to -2. But that probably doesn't surprise you. A few more things I want to do. I want to talk to you about what specific heat is, because I just realized that you probably have forgotten what specific heat is. So our specific heat is really just the amount of heat required. Let's write this down right over here. This is the amount of heat, required to raise 1 gram of a substance 1 degree Celsius. So the amount of heat required to raise 1 gram of a substance 1 degree Celsius. So let's just talk a little bit about specific heat and what it means. If something has a high specific heat, that means it heats slowly because it needs a lot of energy, right? If it has a high specific heat, that means it needs a lot of heat to increase that temperature. So that object is going to heat slowly and it's going to cool slowly. It's going to do everything slowly. And why? Because it takes more energy. The substance with the highest specific heat is liquid water, which has a specific heat of 4.18 joules per gram degree Celsius, and that's liquid water. Now, something that has a low specific heat. This is something that heats quickly, but it also cools quickly. So it heats quickly and cools quickly. Why? Because it takes less energy. It takes less energy. The object in your reference tables that has the lowest specific heat is lead, which has a specific heat of 0.13 joules per gram degree Celsius. Now, how does this affect us? Well, if we live here on the beach, it's my dream to live on the beach. If I hit it big, that's where I will live. Not a big house, just a little cottage on the beach. So let's think about this for a sec. If we have water that has a specific heat of 4.18 joules per grams degree Celsius, and we have the beach, which actually has a specific heat of about 0.8 joules per gram degree Celsius, then which one's going to heat up faster? Is it going to be the water, which has to save up more energy, or the beach that has to save up less energy? Well, the beach will heat quickly and cool quickly, and the water will heat slowly. So when you saw this last, you probably saw it during the sun, during the daytime, when the beach heated up and that hot air rose over that beach and cooled and sunk over the ocean, and a convection cell set up over this beach. And what you probably saw was what's called a sea breeze, where the air blows off of the ocean onto the beach, and this is as wind, right? Because of the convection that occurred simply because of the different specific heats of the beach and the water. So because the beach has a lower specific heat of around 0.8 and the water has a higher specific heat at 4.18, that makes this beach heat up faster. That heat rises and sinks over the cooling water, causing the wind to blow in off of the ocean during the daytime. And we even flipped that and we said, you know what? At night, when that sun goes away, then this is our hotter spot, right? Because if it heats slowly, it also cools slowly. So at night, this actually reverses. And it's simply because it also cools slowly. So this water cools slowly, and at night, this is that area of heat. The hot air at night rises over that water, and then the breeze reverses itself during the nighttime. So at nighttime, we get what's called a land breeze. And this is all due to, you got it, specific heat. This is all because of different specific heat. So I hope that makes sense to you. There's just one last thing, and then I promise I will stop talking. And that is, how do we use these heat of fusions and heat of vaporizations? So this one right here, just to give you one more equation, you need to know this Q equals Cm delta T to do something for me. And then you also need to know Q equals M times the heat of fusion. And this is, by the way, 334 joules per gram. That's this. Oops. This is the heat of fusion right here. All right. And then there's one more equation, Q equals M times the heat of vaporization. And that's this one up here. It's the 2,260 joules per gram. So real quick, if we did this, if we just took a 100-gram sample of water, let's do that. Let's take a 100-gram sample and we say, all right, how much energy, can you see this? How much energy is required to melt 100 grams of ice? All right, so we do this equation. Q equals M times the heat of fusion, because that's for melting down here. That's the heat of fusion right down here. So we would just do Q equals 100 grams times 334 joules per gram. And that's a pretty easy equation because it would just be 334 with 2 zeros at the end for the 100, and that would be joules. So it would be 33,400 joules. Let's contrast that to how much energy is required to evaporate 100 grams. So how about the evaporation of 100 grams? So we would do the same thing. Q equals M times the heat of vaporization. I'm not even on the screen. Sorry about that. Q equals M times the heat of vaporization. And in this case, it's still 100 grams because we're still working with a 100-gram sample of water. But the heat of vaporization is this one right over here. It's the 2,261. So times 2,260 joules per gram. So Q equals 2260 plus the 2 zeros from the 100, and that's a measure in joules. So it's 226,000. So you can clearly see that it takes more energy, a lot more energy, to evaporate water than it takes to just melt water. And that's why over here on this graph, this is 226,000 compared to 33,000. That's why this line is so much longer, because it takes so much more energy to evaporate water than it does to just melt the water. All right. So again, I will go ahead and show this equation sheet to you and post it. But that is enough, I think, for you to, I'll just turn this sideways real quick. That's enough for you guys to get to where I need you to be. I hope you're all doing well. Take care. Bye.